Okay, so this particular set of problems is related to our friction, and we just didn't have enough time in class to really talk about it. So I wanted to at least look at the idea of question number one, and then you can take a look at two and six on your own because those have some keys posted for them. All right, so let's read through this. Coefficient of static friction between a stationary box, so stationary non-moving box, got it. And this is static friction, so that makes sense. And the floor is zero point 0.6. If the box has books that weigh 150 newtons stacked in it, and the force applied is 45 newtons horizontally on the box, calculate the force of friction. All right, I got a lot of information there. So I'm going to start with a visual. When we're going through this, you always want to start basically with a free body diagram. Now it's a box. I probably should just draw a dot, but I want to kind of make some sense out of what I'm seeing. So I got a box on a surface. Therefore, there's no angle involved or anything it says in there. I got to have gravity working down against the surface. We'll have a force normal that's pushing up. And then we have this force applied. I'm going to call the right my positive direction, just because that's generally what happens on a number line. Now, the force applied is actually given to us, so I'm going to jot that in. It's 45 newtons. Other than that, of course, opposing our motion from that surface part on there would be our force friction, and that is actually what we're trying to solve for. So now we're going to dial in and sort of take a look at what all this means. Keep in mind, there's kind of two things that could be happening here. My force applied is only 45 newtons. If the force of friction relative to the normal force and everything else on there is bigger than that, then the box might not move at all. And we'll talk about what that situation means. What most of us will probably do is jump to our equation sheet and realize, okay, force friction is going to be our coefficient of friction, in this case static, times our force normal. We have to realize it's not truly an equal sign. We write that a lot just because we're talking about something that's already in motion, and so we're going to have this minimum situation involved. But when we really talk about this, especially from the static perspective, it's less than or equal to. So force normal mu would be that value that you have to overcome to actually have the force friction, bypass what that motion would actually be opposing against. So I'm going to start there and just kind of think, well, what could that be? Like, what could be our highest value that we're looking at that the force friction has to be less than or equal to? And if that's the case, we have to figure out what our force normal is. Luckily for us, it tells us our mass right here. So force gravity should just be mass times g. I don't theoretically know my mass. I know the mass of the books relative to gravity. And assuming the box doesn't have an additional mass to add into, we're going to go ahead and say this is about 150 newtons. Now, the box may have some mass that we'd actually have to include, but the problem didn't provide it. So for the case right here, I'm going to say, okay, let's just call it 150. If that's the case, the box is not accelerating. We have a net force of, net force of 0 in the vertical direction. The box is not accelerating up or down, it's just sitting in place. So that would indicate that our force normal is, of course, 150 newtons. Now, we've been writing this out differently. We'd say, like, okay, the force gravity minus the force normal, that's got to be set up equal to 0, but I'm just trying to do this with generalized arrows for you right now. What's helpful now is because I know my force normal and I know my coefficient of friction, I could solve for what that force friction should be. So our force friction needs to be less than or equal to 0.6 times my force normal, which is 150, which means my force friction needs to be less than or equal to 90 newtons. Now that's interesting, because if we think about that, my force friction is less than or equal to 90 newtons. Well, let's think about the case situation that we have. The force applied is 45. So then what's your force friction? Well, it would only be 45 newtons. I mean, if you're pushing with 45 in one direction and friction can get up all the way to 90, it's going to be less than or equal to 90, in this case, 45 newtons, which means the object is not going to move, which gets you a 0 acceleration because the object is just still sitting in place. So for the purposes of this problem, like, we're looking at this from the perspective of this problem is not going to really be too tricky, in that the 45 newtons is really just being pushed into one direction. One last little detail as you're looking at this in this particular problem, if you look at the answer key, there's an entirely new way to set this problem up because the word stationary was added to this problem. In the old version, we just had the idea that there was a box. And so if that box had been moving, this entire problem would be set up differently. The force of friction would actually be bigger than the force of applied, and we'd have a negative acceleration in the opposite direction, which doesn't make too much sense, but we could end up solving for all the math in there. So in case you are checking the answer key. All right, the answer key is a little bit incomplete on this particular one, so I also want to just do number two. Again, feel free to increase the speed on the video recording if you need to. All right, so number two, a force of 4 newtons is required to pull a block across a level surface at a steady rate. That's going to be really important here. Steady rate means acceleration is equal to 0 or net force is also 0. Okay, so the force pressing the surface together is 18 newtons. Force pressing surfaces. Okay, so force normal is what we're talking about there. Let's go ahead and calculate the force friction. So like anything, we need to start with a picture or a free body diagram. So we've got this block being pulled across a surface. So there is a force applied. In this case, that would be 4 newtons. We have force gravity working down. We have force normal working up. And as we look at that, we're like, okay, cool. Do I need all this information? And then force friction is working against whatever we're doing in the positive direction, which I'm calling, to the right. All right, with this in mind, calculating the force of friction, here is the key. Force, our net force inside of here is a net force of 0. So if you have an applied force of 4 newtons, guess what your friction is? Also 4 newtons. So if that's the case on this, it makes solving the rest of this problem a little bit interesting because we're not doing it in quite the exact same way. We're going to look at this almost kind of in a backward situation. I actually know the force of friction should be equal to less than or equal to our coefficient of friction, in this case, which would be a kinetic one, times force normal. We're trying to solve for this coefficient of friction, and so as we do that, we actually are going to need something else besides, the force of gravity in this case. And so a lot of kids will look at this problem and be like, oh, I don't know what my force of gravity is. It's like, yeah, I know we don't have the mass, we don't need that on there, but we know our force normal already. This problem is so easy, you will overcomplicate it. Your force normal is 18 newtons. Your force of friction, you just found out, was 4 newtons. So all we have to do now is set up and try and solve for that mu. And so I would basically say 4, and I'm going to just flip over to equals to make my life a little bit easier here, is equal to my coefficient of friction times 18. And so our coefficient of friction, in this case, is going to be 4. Ooh, I got a little wild. 4 over 18. And so if you type that in your calculator, you'll end up with your answer in that case, but that's all we have to do. One thing to keep in mind, since both these forces are measured in newtons, there is actually no unit involved for the coefficient of friction. So if you were solving something like this, it's really quite simple. We didn't even measure force gravity or anything else on there. We could work backwards to figure out the mass. If we just said, okay, well, if the force normal is 18 and we're not, flying through the floor or accelerating into space, we know force gravity is mass times, 9.8. And so if we know the force gravity is 18, we also could go through and solve the mass. That's something else the sheet does on here. The other question to take a look at is number 6. That key is a little bit more developed, so I feel like that'll be an easier one to follow. All right, last but not least, in class on Wednesday, I was missing a lot of people, but we did talk about kinematics and forces when they come in together. So this is just question number 3. If you're in class this day, you already saw this one, but I wanted to make sure I had time to go over it with people that were not, just so you guys could actually see how to run through a couple of these, because you'll see this on the quiz. So in just reading through this, a skydiver has a speed of 36 meters per second. We're just going to ignore this mile per hour stuff. It really is irrelevant. When he pulls the parachute, skydiver has a mass of 90 kilograms, which is about 200 pounds. Don't really care. If we assume the parachute provides a constant upward force of 1,000 newtons, how long will it take for the skydiver to reach a velocity of 0 meters per second? How far will the skydiver have fallen in this time? Okay, so like anything, it's kind of trying to understand like what we're actually witnessing. So we have skydiver that is, jumped out of plane, but also has, parachute. Wonderful parachute. Look at that. And if we were going to go ahead and draw like a free body diagram on what we're looking at here, we've got, of course, the force of gravity on the skydiver forcing its way down. And then we've got this opposite force of the skydiver. And if I want to really connect it to our system, it's the skydiver. We have like this force drag from the parachute. Now we do know that force drag is equivalent to 1,000 newtons. We also have some other things on here. And as a reminder, way back when, we were using this thing called the guess method. And the guess method was not guessing, but giving your givens, your unknowns, your equation, substituting, and actually solving the problem. That's what each one of those things on there. So I'm going to just start with what the problem is giving me to try and figure out if I can see, like, is there an equation I can go for? So initially, the skydiver has a speed of 36 meters per second. Got it. So that would be like a velocity. 36 meters per second. Of course, it just says a magnitude for speed, so we don't really care positive and negative in this case just yet. We also know the skydiver has a mass of 90 kilograms, which may not be totally obvious as to what we're supposed to do with that just yet. So in the parachute, we've got our force drag. I labeled that on my diagram right here. And then we want to know, okay, if the V final is 0 meters per second, the first part is saying, okay, well, how long will it take? So I'm trying to figure out, my unknown piece is what the time is. Yes, there's a second part for the delta x, but we'll worry about that later. Okay, so with this all in mind, we have to kind of figure out what did we do first unit with kinematics. And in kinematics, we had three basic equations. We knew the velocity final was given by velocity initial plus acceleration times time. We also knew that, x final is given by the original position plus v0t, 1/2 at squared. And we knew velocity final squared is given by velocity initial squared plus 2a delta x. So those are your three kinematic equations that are on your AP1 equation sheet. Now, the only equations we've actually messed with since then have been the acceleration of a system is given by the net force on that system over the mass of the system, or what we often refer to as F equals ma. We also have one other equation we've used, which is, that the force of friction is less than or equal to the coefficient of friction and the force normal. Yeah, that's not really going to come into play here. We're not really talking about friction at all in this problem. So when we look at this, if I'm trying to figure out time, I have a few options. I don't really have a distance, so that's not going to be super helpful. I'm going to use the second equation, which again means the third equation is not going to be super great. We're really trying to spot this one. And if that's the case, I'm trying to solve for t, well, I better use acceleration. Now, here is the part that people will mess up. Every time we did kinematics in free fall, we were talking about something that was accelerating with the value of gravity. We would say, hey, the acceleration is just equal to gravity. That's not true in this problem because we have a free body diagram that's telling us our net force is not going to be equal to 0. Well, maybe it is. I don't know. I haven't actually solved for it. It's the first question. So we actually have to start down here and figure out, F equals ma. What's the acceleration of the system? I'm going to call downward direction as my positive direction, just because I feel like that's the direction the person is going. And we talked about the skydiver's speed of being 36. I'm assuming that's going down because that's usually what happens when you skydive. So when I think about my net force for this particular diagram, I'd say, okay, well, the force of gravity is going in my positive direction, and it's going to be subtracted from my drag. My force gravity would just be the mass of the person times 9.8, and the mass of this person is 90 kilograms. So if I have a 90 kilogram person times gravity minus 1,000 newtons, I can actually set this up and figure out what the net force on my system is. Now, the net force on this system, as we go through it, 90 times 9.8 minus 1,000. I'm going to go ahead and type that in really fast. We have, okay, 90 times 9.8 is 882 minus 1,000. And I get a net force of negative 118. And you're like, net force of negative 118? How can I have a negative net force? Well, if you think about it, which direction is the force actually working? Up. Like we are forcing this object up, which means the acceleration is also going to act up because you're slowing down. If 36 is our positive direction and we're going to reach 0, that's why acceleration is actually going this way or in the upward direction. So from this, we can actually use Newton's second law and say, well, what is the acceleration of the system? Our acceleration in this case, we would have negative 118 newtons over the mass in this case, which is 90, and we'll have a negative acceleration or an upward acceleration in this case of 118 divided by 90, about 1.31 meters per second squared. Okay, so now what on earth do we do with this? And that should be negative, sorry, because we are going in the upward direction. Well, if we have the acceleration, we have the original velocity and the final velocity, we could figure out the time. This first kinematic equations makes life actually pretty easy to work with. So my final velocity is going to be 0. My initial velocity was 36 meters per second in the positive direction, so we called that down, plus negative 1.31 meters per second squared times time. Okay, so I'm just going to add that on to the other side algebraically here. So I got 1.31 t equals 36. Time is going to be 36 over 1.31. And yes, there's units associated with this, and so we'd end up having meters per second over meters per second squared, and we're going to end up with just seconds if we cancel those out. So 36 divided by 1.31, we end up with about 36 divided by 1.31, 27.5-ish seconds. And so that means this person is in free fall for about 27.5 seconds. Now, it's not truly free fall because we are accelerating. It just means they're dropping down from their parachute, because we have an upward acceleration in this case, which is why we actually get that time. The second part of this problem says, well, how far is that person going to be, accelerating upward as they travel down? That we go back to our kinematic equations and look at the ones we crossed out. You have two options. You could work with the second kinematic equation, call this delta x, and then plug in your times there, your original velocity. You also could work with the third kinematic equation, and we would just solve for the delta x using that setup. It doesn't really matter how we set this up. I just tend to avoid, if time's in two spots, I don't really want to plug it in because I really solved for that. I don't want to plug in the thing I just solved for in case I make a mistake. So I'm going to use the third kinematic equation. Velocity final squared is equal to velocity initial squared. Don't mind the bell.
Good morning.
Okay, so now that the bell is actually gone to a delta x, and we are trying to find our delta x in this case. So the final velocity is going to be 0 for my substitution here. My initial velocity is 36 meters per second squared in the positive direction, so I'm going to call that positive, plus 2, and then our acceleration was negative 1.31. If you called upward positive, then your signs are obviously going to be flipped here. It's really not important which way direction you called positive, just that you have your signs annotated in a way that they're going to cancel themselves out. And so delta x is what I'm trying to solve for. So I'm going to go ahead and do some algebra here. So I got 2 times 1.31 delta x. So I basically just added that to this side. I put the negative in front. We're adding it to this side. Is equal to 36 squared. So delta x is going to be 36 squared over 2 times 1.31. And if you don't like all that algebra at once, you can just solve it a little bit faster, or you can solve it a little bit longer if you'd like to. So 36 times 36 divided by 2 divided by 1.31. And we get an answer of about 495, which should be in meters because I'm in meters per second. And then down here I'm in meters per second squared, and the 2 has no unit associated with it. So if you actually were to cancel the units out, that's how we end up this way. The reason why I wanted to go over this one with you is this is kind of combining unit 1 with unit 2, and this is a lot how AP tests will do it. They're not just going to ask you about a free body diagram. They're going to say, hey, now that we know the free body diagram, the acceleration of the system, how can we actually go further with this and take this to the next spot and combine the two together?